Okay, we got recording.
Hello. Hello.
Hello?
Hello. So just so you know, we are recording. Everybody can hear me?
Yeah.
Yeah.
And now I'm really curious. So did everybody hear the music earlier while you were waiting?
Yep.
Sure did.
So I actually got that to work. Okay, so I'm gonna share my screen. Yes, and now you know something about my sense of humor if you didn't already. Okay, so I'm gonna share my screen and we're gonna get started. And as my wife points out, I hope I've closed all my really embarrassing browser tabs. Okay, so is everybody as ready as they're going to be? Just say yes.
Yes.
Yep.
Thank you.
Yep.
Okay, so now let's try mics off until such time as I ask everybody to turn the mic on. Okay, so right. Oh my God, I'm going to start with writing something. So here goes. Last time we talked about the parity check code of length n+1, and the idea is, okay, let's see if I can actually write something. There we go. All right, so the idea is if you have some, let's try if we have a message. So suppose we want to send the message. You know, one good thing I've discovered, this is my second time trying this now, I discovered is that I now write so slowly that you might actually be able to follow. So if you want to send 4 message bits, 1011, then does anyone remember? Then we're going to transmit. Let's see if I can actually write with my finger. It's a little faster. We're going to transmit not just 1011, but a parity check bit in the front. So on the count of 3, let's see if we can do this count of 3 thing over the internet. On the count of 3, can you say what the parity check bit will be? 1, 2. You can either say on the chat window, or you can turn on your mic and say out loud. What will the parity check bit be? 1, 2, 3.
1.
Good. Right, and it's the parity check bit is 1, because the sum of the message bits is 1 mod 2, or in F2, as we prefer to think about it. And the idea is that so if something bad happens in transit and the receiver gets, for example, 1 1 1 1 1 1, then the receiver will say that, oops, the sum is 1 mod 2. So the receiver knows something went wrong. So this scheme, so parity check detects 1 error. Oops, 1 error. Okay, so everybody remember that from last time. You can either say, you just say Y on the chat. You know, I'm going to try doing this with, this is actually a very typey kind of thing, so I'm going to try typing some more. So the repetition, so last time we also saw that the repetition code of length 3 corrects 1 error, but corrects 1 error as follows. So here, your message is going to be just 1 bit. Let's say the message is going to be 1. And then what you do is you set, well, actually I just do this twice. So if your message is 0, then you transmit 0 0 0. And then if you receive, say 0 1 0, then the receiver reasons that one error is more likely than two, so the most likely intended message transmission is 000. So the receiver will then decode the message as the intended message as 0. All right, so that is how, so the idea here is that we somehow have one error in transit. When you leave your mic on, I can hear you yawning really loud. But I'm sure you can hear all kinds of crazy noises that I'm making. We're all going to get to know each other a little bit better, huh? All right. So sorry. This demonstration shows you that if you have one error in transmission, then the receiver will be able to figure out what you meant because you said it 3 times, and probably the thing you said twice is what you meant, and not the thing you said once. So are there any questions about either the parity check code of length n+1? Oh, this thing I just drew here is n. Just to be clear, n equals 4. So here for the parity check code, I think it makes more sense to use the notation where the length is n+1 because there's sort of n regular bits and 1 parity check bit. Anyway, so are there any questions about the parity check code of length n+1 or the repetition code of length 3? Yeah, by internet, the silence is even more awkward than it is in person, huh? So is oh, all right, Fan, can you turn on your mic and sort of say just a little bit more about what you mean by explain the parity check again? Oh, you have no night. Can you say a little bit? What would you like me to explain about the parity check? Does it make sense where the extra bit comes from? Yeah, so Than is asking, can you explain about the parity check again? But has no mic. Can you just say again why it is that what can you articulate what it is, or would you like me just to repeat it again? Oh, the transmission part. So this is the intended message. So the distinction here is between the intended message. The thing you want to send is 1011. For whatever reason, you want to tell your friend 1011 is the secret code for today. So does that make sense? Stan says yes. So what you actually send your friend, instead of just sending 1011, is 11011. So this is the thing. This is the part that you actually. This part here is what you actually transmit. So instead of sending just those 4 bits, 1011, you send 5 bits, 11011. So does that make sense so far? And okay, great. So Stan says okay. And so what happens is that when you send a message by like internet or by wireless or whatever, communication is not perfect. Like every once in a while, if you're sending a string of 1s and 0s, one of those 1s and 0s will flip from a 0 to a 1, or a 1 to a 0. And what we see here is that the 3rd bit, the thing that the 0 that you're transmitting over here in transmission becomes a 1. So this is sort of a hypothetical error that might occur in transmission. So does that make sense? Yeah, and so right, and so the point is that we have five. The receiver receives 5 ones, and John V asks, why is the sum 1 mod 2? Well, the reason the sum is 1 mod 2 is because, well, you have an odd number of ones. 1 plus 1 plus 1. You have 5 ones total for the received word. 5 is odd, and so mod 2 you get 1, and so that's why the sum is 1 mod 2. And so the receiver knows that something went wrong because the parity check code is designed so that you will never transmit an odd number of ones. Any block that you send has to have an even number of ones, and so if you receive an odd number of ones, you know something has happened in the middle. Does that make sense as to why the sum is 1 mod 2? Okay, great. Obviously, I should slow down this much in real life, for what it's worth. Okay, so are there any other questions about either the parity check code or the repetition code from last time? Okay, thank you very much for your questions. This is very helpful. So the motivating problem is that so this is great. We figured the repetition code tells us how to correct one error out of every block of 3. And so, but the problem is it slows down our transmission rate, our rate of communication, by 1/3. And so the question is, can we do this cheaper? Is there some way we can achieve error correction while sort of having fewer transmitted bits per message bit? And so that's to do that, we're going to look at like a little bit of general theory, and then we're going to look at the most wonderful example, like it's sort of the birth of all error correcting codes. It's the Hamming 7 code. Okay, so here goes. All right, so in order to talk about the Hamming 7 code, I want to talk about just a little bit about codes in general, and then we'll more or less quickly get back to something specific. So remember, so just for terminology, or at least maybe not so much for terminology, but in order to fit what we were doing before into this theoretical framework. So we think of bits as being elements of F2, because remember, it's, as I keep saying, the thing that ensures that I have a job, or one of the things that ensures that I have a job, is that bits are 0 and 1, and F2 contains exactly the elements 0 and 1. And a bit string of length n is an element of F2 to the n. All right, instead, written horizontally, usually by custom. For example, you would write 0, 1, 1 instead of an 8x1 column vector. And that's just because that's just purely for typographical reasons. And through custom, we've sort of gotten used to writing horizontally, and so it's much easier to write 0, 1, 1, 0, 0, 1, 0 instead of an 8x1 column vector where you go like 0, 1, 1, 1, 0, 0, 1, 0. I mean, we will actually do some of that when we're doing a little bit more linear algebra, but usually bit strings are written out like that. Okay, so that's what bits and bits. That's the connection between what we were talking about before and what we're talking about now. So now what we're talking about, so the idea, the first definition to absorb is the definition of code. So a code is a subset of F2 to the n. Oh, shoot, I forgot to say, not just a code. A code, this is going to work. A code of length n, that is. Length n. Actually, I should say a binary code of length n. It's binary because it's over F2. Binary code of length n is a subset of F2 to the n, and so so it's it's a subset, just meaning exactly that. So some vectors, some bit strings of length n are decreed to be okay, and some of them are decreed to be not. So the elements of vector of a code are called code words, and we think of the code words as the words that are possibly that they're the messages that could possibly be correctly transmitted. So I feel like I should write down an example here, but I can't remember if I did this later on. So for example, for the repetition code length 3, the code C contains exactly the bit string 0, 0, 0, and 1, 1, 1. Because if you are transmitting a 1-bit message using the repetition code of length 3, there are only two possible things that you could possibly, there are only two bit strings of length 3 that you could possibly send intentionally. The whole agreement is that you only ever either send 0, 0, 0 or 1, 1, 1. And so that's what I mean by subset of f. This is subset of f here, f of f2 to the 3. That this sort of tells your receiver that I'm only ever going to send you 0, 0, 0 or 1, 1, 1, and if you get something else, that's a mistake. Yeah, so that's the basic idea of a code. Like you agree beforehand, you agree on sort of a coding system, and that coding system tells you what are the possible, at least at first, the first thing it tells you is what are the possible correct things that might possibly transmit, and meaning everything else is an error. It must include some sort of error. And in particular, the codes that we'll be most interested in are binary linear codes of length n, and those are the codes that are not just subsets of f2 to the n, but actually subspaces. So, how are we doing so far? Any questions so far? Great. Was there a reason I chose 0, 0, 0 and 1, 1, 1? Because those 0, 0, 0 and 1, 1, 1, those are the only because that's what that's sort of. I'll type it in. I'll type it in the chat, and also by I'll say it out loud. That's by definition of the repetition code. Repetition code. That's all you ever send if you're using that code. All right, so Ryusei asked an excellent question. Is there a reason I chose 0, 0, and 1, 1, 1? Because under the scheme of the repetition code of length 3, the only things I'm ever going to send are 0, 0, 0 if my intended message is 0, and if my intended message is 1, I will transmit 1, 1, 1, but I will never send anything else on purpose. Everything else represents some sort of error. So Ryusei, does that make more sense? Okay, great. Any other questions? Okay, so now, as is customary, actually, if anybody here is attending today is in 146, you'll recognize that there's always one of these sort of schemes where you sort of give people's names, and so here we go. So I guess for whatever reason, I prefer to use the names Xavier. So we have somebody named Xavier who's sending a message, and Yolanda who is receiving a message. So everything over here on this side is sort of Xavier stuff, and everything on this side is Yolanda's stuff. And then Xavier wants to send a message to Yolanda, and here's the sort of so basically we have this sort of setup. So because we are going to need some sort of standard way of describing what happens of this process when you sort of send an encoded word and hope that the other person gets what you intend. So our sender's name Xavier and our receiver's name Yolanda, and the idea is that here's the procedure. In general, Xavier wants to send some message M, which I should say what that message M is it's a bit string of some length. Let's say m. Say well, let me use m. A bit string of some length of some I don't know, of t. I don't know. So it's a bit string of some given length, and the idea is that in order to send that message of some given length, Xavier will somehow encode m to a code word x, and so this is a bit string of some other length, or maybe not. There we go. And this is a bit string. If I get this right, a bit string of length n. Okay, so usually n will have to be longer than bigger than t. So the right. So for the repetition, actually for the repetition, let me over in blue here sort of indicate what happens here for the repetition code. Over in the column on the side here. So when Xavier wants to transmit the message 0, he encodes that message into a code word, which in the repetition code would be 0, 0, 0. Then he transmits that message x, and Yolanda receives a message y, which might say be 0, 0, 1 if there's some error in the middle. If that last bit got sort of garbled and it came out as a 1 instead of a 0, and then Yolanda, I won't correct my spelling here. Yolanda decodes that received message y as m prime, and success means that m prime equals m, is equal to the message that Xavier intended. So usually this will be in 2 steps. So so the first, so in the case of the repetition code, Yolanda might say, oh well, 001, that can't possibly be what Xavier meant, and there are 2 zeros and a 1, so it's more likely to be 0, 0, 0 than 0. It's more likely there was 1 error than 2 errors, and so probably he meant 0, 0, 0. And so then she'll say, well, okay, that means that the message he's trying to send me is 0. All right, so does that make sense? This is sort of what as a sort of like who, like, yeah, what do I want you to get out of this? Okay, so does that make sense when what I mean by that Xavier is the sender and Yolanda is the receiver? Does that make sense? Okay. Good. And so that's so getting a lot of yeses here. And so then the process is M is the thing that Xavier wants to tell Yolanda, and in order to do that, he changes that thing into some other slightly different form, perhaps in this case just by saying it repeating it 3 times. So does that idea of encoding make sense? Okay, and then so then, as always, when you the whole purpose of error correcting codes is the precept that sometimes when you transmit things there are errors, and so Xavier transmits X, and our standard notation is that the bit string of length n that Yolanda actually received is called Y. So if there are no errors here, then you get in that stage, then Y is equal to X, If there are errors, which is sort of the interesting case, which we have here, is that y is not equal to x. And so this here, the 0, 0, 0 is x, and the 0, 0, 1 is y. So so does that make sense? This idea of transmission and then a different vector for the errors. This is a little slower, so maybe does anybody have any questions about the difference between what Xavier transmits and what Yolanda receives? So for then a 4.1 y prime, yes. And Ryusei asks, in this particular example, y prime is equal to x, and yes, that's what we hope. So yes, I'll type that in chat. Yes, y prime equals x when we successfully decode the received message y. Anyway, yeah. So yeah, or sorry, when we successfully correct the message y, the received message y. Okay, and it's certainly the case that if we are able to correct y to y prime, and y prime is what Xavier meant to transmit, then we'll be able to sort of read y prime and get the correct message m prime equals m. Whew. Okay, so are there any questions about this notation m and x and y prime and m prime? I must make sure everybody's alive out there. Everybody turn on your mic if you can, say yes.
Yep.
Yes.
Yep.
Okay, great. Everybody's alive. So next slide. Bing. Oh, right. So there's a small but important bit of linear algebra here. Right. So let E be the okay. Let me scribble here. So let E sub I be the vector that has a 1 in coordinate I and other coordinates 0. So you may recognize this as the standard basis vector. Look, I made it a nice one. My handwriting is improved by us going online. There we go. Oh no, I made it. My handwriting is not entirely improved. Okay. So there we go. So what I want to make is some dots here. Dot. There we go. So yes. So the E sub I is the vector that has a 1 in position I and a 0 every place else. So I hope you remember, if you've taken linear algebra, I hope you remember that from linear algebra. And so what happens is so if you want to model the process of flipping bit I algebraically, then we say that, remember, y, which is the received vector, y is the received vector, is equal to x, the transmitted vector, plus E sub I. So briefly, so to say that, to explain that in a sentence, that's because adding 1 changes a 0 to a 1 and 1 to a 0. But I kind of see that maybe I should do an example of that. So let me do an example of that down here. So if we're transmitting the message 111, so this is again going to be the rep code of length 3. If I can get this to behave. This is again the repetition code of length 3. And so Xavier sends the bit string 111. If the point of all this, of this scheme that I'm describing here, is that if I'm flipping bit 3, so this is the vector E3. If I can actually draw it, E sub 3, there we go. So the vector E sub 3 is 0, 0, 1. And if, oops, I'm sorry, I don't know why that does that. Still working out the bugs here. Please bear with me. There we go. So if I add, if Xavier transmitted 111 and you get the error E3 happening in the middle, if you add up the entries, you get 1, 1, and then 0. So here is the X that Xavier sent over, and the vector 110 is the Y that Yolanda received. So the procedure that I just wrote down here, this models flipping bit 3. It's an algebraic model of flipping bit number 3. Yeah, so let me repeat that again. Adding the vector E3 is our algebraic model for what happens when you flip bit number 3, because that's exactly what happens. So, and more in general, if you adding the vector E sub I is an algebraic way of expressing what happens when you flip bit number I. And similarly, if you have two, actually, yeah. So adding the vector E sub I is what happens when you it is an algebraic expression, an algebraic way of phrasing what happens when you flip bit number I. So does that make sense, or are there any questions? Okay, hopefully everybody's at least willing to go on. And so in a similar way, if you have two errors, and you flip bit number I and bit number j, we model that algebraically by saying that the received message y is equal to the transmitted message x plus e sub I plus e sub j. And so yeah, so there's that. Okay, so any questions about how the linear algebra of errors? I'm really curious to see what this looks like on YouTube. Like when we have these awkward silences, is my picture going to be on this? I'm actually kind of. Can you guys see my picture? Yes or no? Ah, boy, I shaved and everything. Kyle, what picture? Yeah, okay. Yeah, well, at some point, that's fine. I think my family would say no one needs to see your face, buddy. Okay, moving on. All right, so now I have to the next item on the agenda is to describe is to tell you how people generally describe oh, so there's always there's one question about the error. Than has a question. I have a question about the error. There's always an error if the code is not repeated. So if and the answer is if we are using the repetition code scheme. Yes, that's true. So so the whole point of the repetition code is that the only messages that we ever send, if we are Xavier, the only messages that we ever send Yolanda are either 000 or 111. So if Yolanda gets something else, if Yolanda receives 110, then she knows something went wrong because the thing we sent her was not repeated 3 times. So yeah, so there's always an error if the code is not repeated in the repetition code. As we'll see, that's not an efficient way to do things, and so that's not true in general. So does that make sense? Does that answer your question? Okay, great. Thank you thanks everybody for playing along with us and asking some excellent questions. Okay, so now I want to talk about, so in order to have some scheme that's more complicated than the repetition code or the parity check code, probably the most convenient way to go about this is to use some linear algebra. So let's see, how do I set this up? Yeah, and then all right. So I'll talk about this in general, and then I will go to examples. So all right. So definition. As always, it's definitions, right? So let G be an n by k matrix over. Oh yeah, I guess I should draw a picture of this. So let G be an n by k matrix over F2. So if here's G, if I can actually draw this, yeah, here's G. So I want you to remember this is height n and width k. So and the reason I wanted to emphasize that it's height n and width k is that the columns have height n. And so to say that G is the generator matrix of a binary linear code of length n means that the code C is exactly the column space of G. In other words, the sort of acceptable code words are exactly all possible linear combinations of the columns. So that's what it means to say that G is the generator matrix of binary linear code. Now, if you absorbed all the stuff about column spaces, which, okay, it takes a while, and certainly doing the homework will help with that. But if you absorb all the stuff about generator matrices, about column spaces, this means that usually what you want to do is you want the columns of G to be linearly independent, because then they form a basis for the column space, and we didn't really need the other columns. But okay, well, just to be sort of general, to say that G is the generator matrix of the binary linear code C means that C is equal to the column space of G. So that's what a generator matrix is. Perhaps it's more common. I guess it's probably more common to talk about to describe a binary linear code through a parity check matrix. So let H be a k by n. Oops, and now I want to draw this again. So here's H. So H now here, that is a matrix of height k and width n, so the opposite of what happens in the generator matrix case. So let H be a k by n matrix over F2 to say that H is the parity check matrix of a binary linear code C of length n means that C is precisely the null space of H. So the code words of the code C, sorry, the code words of the code C are exactly those vectors x, such that H times x equals 0. Right. And so, okay, I think now is a good time to flip over to the example. So let me flip over to the example. All right, so let me do parity check first. So, oh no, I forgot to do something. Oh well, I was a little tired when I wrote this. Okay, so let's I think we start off with the parity check code of length 5, which is n equals 4, and so there we go. So when n equals 4. So when n equals 4, then H, write this out, is let H be the matrix with 5 ones in it. 1, 2, 3, 4, 5. So So a very slick way, a very sort of compact and succinct way of defining the parity check code of length n+1 is the null space. The parity check code of length 4+1 of length 5 is the null space of the matrix with the 1×5 matrix with 5 ones in it. And so, in other words, X is a code word exactly when. Oops. So let's try to do this. So X is a code word of parity check code of length 5 exactly when hx equals 0, or if x, if x, x, there we go, x. So does anybody know a good program for writing on PDFs? Apparently, Adobe Acrobat is not one of them. All right, if x is equal to x1, x2, all the way down to x5. So if x is equal to x1, x2, x3, x4, x5, what does that mean in terms of saying that hx equals 0? Well, what does that mean in terms of hx equals 0? That means x. Oh shoot, I did this wrong. All right, so because of the way that the parity check matrix, parity check code works, as we'll see in a minute, it's actually probably better instead of numbering the entries of this vector 1 through 5, I'm going to number them 0 through 4, x0, x1, and then dot, 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 down to x4. And then hx equals 0 is, so I apologize that I'm sort of writing this freehand because I meant to say this, actually write this out, is, well, if I write out if h is this 5 is this 5 by 1 row vector, what does the system of equations hx equals 0 look like? It looks like, well, you can just read it off of the. I mean, you look at that those 5 ones as coefficients in a single linear equation, and you get x0 plus x1 plus dot 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 plus x4 equals 0. So that is actually the defining. So let me go back to the parity check code from the beginning. That is actually the defining, equation. Remember, for whether a transmitted word could possibly be something that was an intended transmission in the parity check code of length 5, 4+1. Remember, we said that we knew that we had an error here because the sum of the 5 bits was equal to 1. And so this equation, hx equals 0, defines the parity check code precisely because it says that, well, your transmission might be correct. The only way, the condition that tells you if your transmission could possibly be correct is whether the sum of those 5 bits is equal to 0. Oh yeah, mod 2. Should let me remind you that everything here is always mod 2. Oops. I will not be able to write mod 2 in there anyway. Well, okay, mod 2. How long will it take me to write mod 2? Okay, there we go. Goodness. Mod 2. There we go. I did it. Fantastic. Okay. So are there any questions as to how and why the parity check code of length 5 is precisely the null space of this matrix H equals 5, a row of ones? Can you guys hear the fire alarm the fire engines outside? That's funny. Okay, well, my bad. Yeah, I live in the Mission in San Francisco, so there's never a dull moment here, huh? Okay, so now that I've verified everybody's still alive, are there any questions about why it is that okay, let me sort of work backwards from this. So does everybody see why the set of system equations hx equals 0 is exactly just one equation, x0 plus x1 plus dot 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 up through x4 is equal to 0? So does this step here make sense as to why hx equals 0 is the same as this one equation? Okay, some yeses. There's nobody. Right. Okay. Yeah, okay. So let me go over it one more time. So H. Did I do something? Okay. I'm gonna put this on the front page. Right. So. Okay. So. Yes. So let me go over that one more time, as requested. So H. Oops. H here is the matrix containing 5 ones. So yeah, Johnny nicely asked if I could go over there. So Johnny, you and me so far. Okay. So so the question is, what does hx equals? So we have a system of linear equations, hx equals 0. And the question is, what does that system look like when you write it out? So does that make sense? Okay, so now let me remind you that we are choosing to number our, I was taking a shortcut, and that did not pay off. So we're choosing to number our variables in a strange way. This first variable corresponds to x sub 0. The second variable is numbered x sub 1. The third is x sub 2. For x sub 3. And x sub 4. Johnny, you still good there? Yeah, I don't mean to pick on you, but you asked the question, so I'm going to see if we can try to have some sort of dialogue here. So, so if those are the coefficients of the homogeneous system of linear equations, hx equals 0, then there's only one equation. It's just because there's only one row, and that equation says exactly that: x0 plus x1 plus x2 plus x3 dot 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 up through x4 equals 0. And remember, it's always, everything we do here is mod 2. That's sort of what makes it work. And so it's important to remember that this is all mod 2. Okay, does that make more sense, Johnny? Everybody, is that are we okay? Great. It's all good, man. All right, so that's how we get that. So returning back to where were we? Here. Okay, returning to here. That's why. Okay, so that's why hx equals 0 is equivalent to with a single linear equation. The sum of our 5 transmitted bits is equal to 0, and so let me remind you that back when we talked about when we talked about the parity check code of length 5, 4 plus 1, remember the receiver knew something was wrong because the sum of those bits was not 0, and so this description that you have a code word exactly when hx equals 0 is a precise algebraic description of the parity check code. So does that make some sense so far? At least some sense, if not necessarily complete sense. Yes, so Than asked, we use mod 2 because it's 0, 1, right? That's right. Yeah, and I guess really the reason that we use mod 2 is because the place where we really use mod 2 most heavily, as we'll see, is actually right here. It's because if we do all of our arithmetic mod 2, then having an error is modeled by adding this vector. That turns out to be the thing that's useful. So is everybody willing to stand put for now with a parity check code of length 5? Okay, then the repetition code of length n is actually specified as a generator matrix. It's generated by the all ones vector, g equals 1 through 1 ... to 1, because we saw when we looked at the repetition. Where's the repetition code? When we looked, here we go. When we looked at the repetition code, the only possible code words are 1, 1, 1 and 0, 0, 0, and those happen to be exactly the linear combinations of 1, 1, 1. And so the repetition code of length n is precisely this the code with generator matrix, the all ones matrix, the 1 by n, n by 1 all ones matrix. Okay. So this is sort of, I mean, this is maybe more like what you've seen before. You specify a subspace by giving a basis for it. But it's not obvious. I think usually it's sort of the parity check matrix scheme seems to be more useful. Okay, anyway, we'll have a more. I think it's actually a little hard to see what's going on because the examples are so. Because these are sort of relatively uncomplicated examples. But are there any questions for now? Okay, so one more bit of terminology. So we had generator matrix and parity check matrix, and now syndrome. All right, so the point of this definition of if you have a parity check matrix for a given binary linear code, then that parity check matrix says exactly that we're happy that if we have some possible transmission, we're happy if h times that possible transmission is 0, and because if we just saw with the parity check code, if that product hx is not 0, that means dot. That means that not 0, if hx is not 0, means there's an error. There's an error of some sort. So the fact that hx not being 0 means an error leads us to the following definition, that hx is the syndrome of x. It's sort of telling you, it's supposed to give some syndrome, meaning this should somehow tell you, this maybe tells you what went wrong, and therefore making you able to correct it. So again, the idea is that if you if that's your syndrome, if you come up with a non-zero h times x, that tells you that there had to be some sort of, if h is the parity check matrix for a given code, when h times x is not equal to 0, that tells you that something went wrong. Doesn't immediately tell you what necessarily, and so you're actually really, your only hope to figure out what went wrong is to look at that syndrome and hopefully diagnose what went wrong. Yeah, so syndrome, like it's like a symptom of a cold, for example, like sneezing is a symptom of a cold. So h sub x is a syndrome of, I don't know, messing up bit number 5. Does that make, well, are there any questions about these 3 definitions: generator matrix, parity check matrix, and syndrome? Any questions about those so far? Can everybody turn on their mic and say, no, there are no questions?
Okay.
No questions.
Thank you. Thank you for reassuring me. Okay. All right, so next. All right, we actually already went looked at the examples. Okay, so now we get to this is like one of my favorite mathematical objects ever. It's pretty awesome. It's the Hamming 7 code. And so remember how we just said that you can describe a code either using a parity check matrix or a generator matrix. And so this code is so excellent that I'm going to describe it in in both ways. So on the one hand, it's true that H7 is the null space of this parity check matrix, with the columns of which I will explain in a minute. It's this matrix here, and it's also the column space of this generator matrix. It's all linear combinations of these four vectors, right? And so you can see, because this column is a 1 and all zeros, this column is a 1 and all zeros. Sorry, this row is a 1 and all zeros. This row is a 1 and all zeros. Same here and same here. We can see that these columns are linearly independent. So let's do a little pop quiz. So the dimension of H7 is, right. So okay. So what do I mean that? So let's try to put some stuff together here. So when I say the dimension of H7, remember H7 is a subspace. It's you can either think of it as the null space of the matrix capital H7 as opposed to script H7. Or you can think of it as the span of that generator matrix, and it turns out these columns are linearly independent. So, somebody want to? All right, so let's try this. So on the count of 3, I want you to tell me either the dimension of this null space or the dimension of this column space, which are the same thing. So on the count of 3, I want you to either type it in or turn on your mic and say it out loud. 1, 2, 3, go! Hey, great! A non-empty response. Great. So a couple people were brave and said that You know, there's you can totally say it on the chat, and I don't think the chat is going to show up in the video that goes into YouTube, and so you're totally safe there. I mean, famous last words, but yeah. So the dimension of H7 is 4 because for two reasons. One, you can see from our generator matrix that there are 4 vectors in a basis. So dimension equals 4, and equivalently, in terms of the parity check matrix, you can sort of oh yeah, because our parity check matrix just happens to be in, if I can ever get this to type, I'll definitely have a better way to do this on Monday. Let's type it over here. So the parity check matrix is in reduced row echelon form. If you look over at capital H7, it's in reduced row echelon form. Look, there's like a leading ones, and what's above it is 0. So great. So the rank is equal to 3. So the nullity, which is equal to 7, the width minus the rank equals 7 minus 3 equals 4. So even if you don't believe, even if without having to believe that that these 4 columns of G7 are actually a basis for the null space of H7, which is true actually. You can sort of G7 is actually what happens when you apply the usual reduced row echelon form solution to this linear equation. H7x equals 0. Oh yeah, I should write that in. So remember, the defining equation of code words is capital H sub 7 x equals 0. So let me put that in words. So remember, x is a code word of Hamming 7 exactly when H7x equals 0. So that's what the definition of parity check matrix says. That to say that capital H7 is the parity check matrix of Hamming 7 is to say exactly that x is a code word of Hamming 7 when H7x equals 0. So this is like this equation here, H7x equals 0, is the definition of the Hamming code. And that's the definition we'll turn out to use. All right, so the key point, so the fun part, the key point of the matrix H7 is that column number I of H7 is the binary digits of I upside down. So what do I mean by that? Here's what I mean by that. So if I look at column 3, so if I look at column 3 upside down, or sort of going from bottom to top, oh no, why would that go away? Upside down is 0, 1, 1. The binary digits of 3. So column number 3 upside down. Column number 3 upside down is 0 and 1, and the binary digits of 3. And so that's that. If you go through the columns of H7, that's true. You know, this is 1, 2, 3, 4, 5, 6, 7. If you go through them, you'll see that it just so happens that one of these great accidents of nature that that you get something interesting. If for some strange reason you want to look at the matrix whose columns are the binary digits of 1, 2, 3, 4, 5, 6, 7 upside down. Okay, so so that's what the Hamming 7 code is. All right, so here's how you encode and decode in using the Hamming 7 code. So suppose Xavier wants to send 4 data bits to his friend Yolanda. So So what the first thing that Xavier does is copies the 4 data bits of M into positions 3, 5, 6, and 7, and the other bits 1, 2, and 4 are defined by the equations x1 equals x3, x5 equals x7, and I mean, so what this is going on here is that what's really sort of going on here in terms of linear algebra is that 3, 5, 6, and 7 are the free variables, and 1, 2, and 4 are the leading variables. And remember, when you solve, so these are the free variables. Remember, so when you come right down to it, this is a solution of a homogeneous system of linear equations, and so these four variables, x3, x5, and x6 and x7 are the free variables, and x1, x2, and x4 are the leading variables. And as what always happens when you solve a homogeneous system of linear equations, those leading variables are determined by the free variables. Okay, so and the idea is that Xavier is going to transmit the vector x, which is the vector x1, x2, x3, x4, x5, x6, x7, and Yolanda receives some other vector y. Maybe y equals x, maybe not. And so here is what happens in practice. So let S be the syndrome of y. If S equals 0, then y is a code word. So Yolanda chooses y prime equals y. Otherwise, Yolanda is going to read S as the binary digits of a number I, and chooses y prime to be y with its ith bit flipped. You sort of change the ith bit, and then so that's how Yolanda corrects y to y prime, and then to read the message off of y prime, Yolanda just reads bits 3, 5, 6, and 7. Okay, so now, oh my God, 8 minutes left. So I'm sure that didn't really make any sense. That's okay. Well, it's not okay, but we'll fix that with an example. So there we go. Here's an example. Okay, so I want somebody to give me an intended message. So what message are we going to try to transmit? Oops, why did that not work? Can somebody just type in, either say out loud or just type it in the chat. Just type in four bits. Any 4 bits, doesn't matter what. Okay, so 1010. All right, so the first step is to copy to bits 3, 5, 6, and 7. Okay, so let me do that. So here's what Xavier is going to transmit. So 1, 2, 3. So we're going to go into positions 3, 5, 6, and 7. 1, 0, 0, 1, 0. All right. So that was step 1 of this process, or the first step of step 1, copying the 4 data bits into positions 3, 5, 6, and 7. So is everybody good? Everybody good with that so far? Oh, I like that. The 2 of you picked 1010 the first time. Interesting. So is everybody good with that so far? Okay, so that's something. All right, so now you fill the sort of empty bits by taking 1 to be the sum of 3, 5, 7. So 3, 5, and 7, bit number 3 plus bit number 5 plus bit number 7 is a 1. So this is so I should just copy down what those is: 3, 5, 7, 3, 6, 7, and 5, 6, 7. So this is from 3, 5, 7, and this is 3, 6, 7. Oops, it's up here. This is going to be the sum of 3, 6, and 7, and the 4th bit is going to be the sum of 5, 6, and 7. 3, 5, 7, 3, 6, 7, 5, 6, 7. Okay, and so 3, 6, and 7 is 0. oops. Sum of bits 3, 6, and 7 is 0. The sum and the sum of bits 5, 6, and 7 is 1. So this is what this is what Xavier sends. Okay, so now we have now we're going to have an error happen in the middle. So so again, I just need somebody to do something random here. So can somebody type which bit you want to get messed up in the middle? First person to type gets to dictate what happens. Okay, so let's suppose bit number 4 gets messed up. All right, when bit number 4 gets messed up, that means, let's see if I do this. The 4th bit turns to a 0, and all the other bits stay the same. Oh, I should have left the other. I should have handwritten the other ones, and I should have printed the other ones and handwritten that one. Okay, and this is your Y that's received. So does that make sense that we have, oops. All right, there we go. So does everybody see what I mean by bit number 4 got messed up there? Are there any questions about that? Okay, the Hamming scheme then says that Yolanda computes the syndrome S equals H7 times Y. Now I'm just going to do this quickly. So what's going to happen here is that S equals H7 times Y. And the thing to remember is that matrix. Yeah, so Than asks, does that mean that only one of the bits can get wrong? Yes. So what we'll see is that momentarily is that Hamming 7 corrects one error, but that's it. So remember the matrix. If you have a matrix times a vector, is a linear combination of the columns with coefficients from the vector. When you multiply a matrix times a vector, you get a linear combination of the columns of the matrix with coefficients coming from the vector. And so S is going to be equal to the sum of columns 1, 3, and 6, which is equal to it's going to be 1, 3, and 6. Just quickly, I'm going to look at it's going to be 1, 0, 1. Oh, 1, 3, and 6. My bad. So it's going to be 0, 0, 1. Oops. So yeah, columns 1, 3, and 6. So if I add those, so Y had S, which is H7 times Y, is going to be H7 times this vector, which has ones in positions 1, 3, and 6, and so H times Y is the sum of columns 1, 3, and 6. And if you add those up, there's 2 1s in position 1, 2 1s in position 2. Those are both 0, and 1 1 in position 3. So we get 0, 0, 1. So 0, 0. Once we see that there's a 1 somewhere in this, that means that there was you immediately detect that there's an error, and so now we read that as 1, 0, 0, the binary digits of the number 4. So Yolanda knows that bit 4 got messed up. What?
Oh, what?
Isn't
Wow.
that crazy?
Crazy.
Madness. So yeah, I think that's not a bad. So I think that's not a bad place to stop. Especially since thank you very much for participating in this experiment. So so next time we will start over here by proving that that always works. That so if you have one error in bit I, then the syndrome that you compute precisely gives the binary digits of I upside down. And then we'll go over the proof, look at the proof of that, and then talk about the Hemming 8 code. All right. Anyway, so I think thank you very much for coming in this time of plague. Thank you very much for being willing to be recorded and participating in this very, very strange situation. We're all going to be okay. Just remember to wash your hands, stay home when you're sick, and
Great
avoid
question.
large social gatherings.
Yeah, YouTube.
So I'm going to let you go now since we're 1 minute over. Thank you very, very much for doing this.
Hey,
And,
Professor.
thank you for having continued patience with me, and I will talk to you on Monday. Oh yeah, and actually I'll let you know sometime tomorrow, if not earlier, how we're going to have a sort of virtual problem session. Okay, bye. Thanks, everyone.
Oh.
Go ahead.
Are you gonna send out a link with the with the YouTube link containing in it later on?
Yes.
Okay, got you. Thank you.
All right. Talk to you later. Bye. Bye, everybody.
What happened?